Now we're going to later come back to our power control and view it as a game. But first, let's take a look at two simple but very famous examples. Perhaps by far the most famous example of simple game theory is the so-called prisoner's dilemma. It's a two-user game, modeling competition, and each user has two possible strategies. So we can plot this in a two-dimensional space, in a table on a piece of paper with two columns and two rows. Okay. Let's say the two rows represent the two strategies for player A, and the two columns represent the strategies for player B. And players A and B are suspects of a crime, and the police is going to investigate into this crime and examine both of them individually. So they are going to know the entries in this table later on, but they cannot communicate because they are being questioned separately. And let's say they have two choices to make. One is you do not confess, no confess. The other is you confess. Similarly, B can also say, I don't confess, or I confess. So there are altogether four possible outcomes. For each of these outcomes jointly determined by A's strategy and B's strategy, there will be a pair of numbers. The first number denotes the payoff to A, and the second the payoff to B. So if they both decide not to confess, then the police can only charge them with a lesser crime, and they will each get, say, 1 year in prison. Whereas if they both confess, then they will be sent to prison for a longer term, say 3 years. Whereas if one confess but the other not confess, then the one that confess will be rewarded and walk away free for cooperating with the investigation, and the other one will be left with a most severe penalty of, say, 5 years in the prison. And this is a symmetric game, so we also have this cell filled out exactly like this one. Okay, if B confessed, then she walks away with nothing, 0 years, and A do not confess, then she will be getting 5 years. Okay, so this defines the game, the prisoner dilemmas game, because there are two players, each has a strategy set consisting of two possible strategies, and this table quantifies the payoff for each player jointly determined by their respective strategies. So let's take a look at this famous prisoner's dilemma. Why is it called dilemma? Because imagine you are suspect A, and you say, I don't know what B will do. But suppose she chooses not to confess, then what should I do? Well, if I don't confess, I guess -1. If I confess, I get 0. So I should pick confess. We call this the best response strategy by player A in response to player B's picking no confession. But B may also choose to confess. I don't know. And in that case, what should I do? Well, I'm basically comparing -5 and -3 here. Still, confess is the better choice. Relative to -5, -3 is better. And therefore, confess is also the best response strategy if B chooses to confess. Now, B can only choose between two choices. So, A would say, hey, I have the same best response strategy no matter what. That is called a dominant strategy. If it is the best response strategy for all possible strategies by the other player. In this case, that is confess. Now, by symmetry, B is thinking in exactly the same way. And B will also pick confess as the dominant strategy. And therefore, the outcome of this game will be that both A and B will confess and get 3 years each. And what's wrong with that? Why is it called dilemma? Because they could have got 1 year each. If you think about the summation of the payoffs, and you want to for each I, maximize this quantity, then -2 would be much better than -6. Except A and B cannot collaborate or communicate. So in their each strategization process, they end up picking a socially suboptimal solution. And that's why it's called a dilemma. So in what we just talked about, we have defined the best response strategy in a game and the dominant strategy in a game. Now there may not be a dominant strategy, as we'll see right away.